This physics video session. In this video, I'm going to talk regarding the atomic structure. In that one, the main contributions of the quantum numbers, right? You know, the quantum number is nothing but a theory which explains about the state of electron around the nucleus, right? A quantum number is a one which explains, right, if you have the nucleus and what is the position, how it is rotating, how it is oriented, everything regarding the electron, right? So this is the orbital, right, the space or region where there is maximum probability of finding the electron, right? Regarding that one, we like to introduce spin quantum number today. Okay, now before talking about spin quantum number, let me talk to you regarding what made the spin quantum number to get introduced. Right, earlier the famous one, as you all know, spin quantum number used to talk or spoke regarding size and energy of the orbit. Right, let me go step by step. Right, if you are talking about, right, so this is nothing but the orbit, right? Principal quantum number denoted by N spoke about the energy and the size of the orbit. This is nothing but the orbit. We know this. The second one, azimuthal quantum number spoke regarding the shape of the subshells, right? So orbit is the main part. In that one, we are having shells, right? Subshells. You know, we know S as the first, S, P, D, F, right? Azimuthal quantum number is talking about the subshells. Let us take this as a P, for example. The earlier one as something like S. Right. Now, azimuthal quantum number spoke about the shape of the subshells. Now, the third one, magnetic quantum number spoke about the orientation of the orbital along the axis. Orbital means we were talking about the one which is inside. The first one Px, the second one Py, third one Pz. We are talking that. So, what I mean to say is principal quantum number spoke about the orbit. Right, azimuthal quantum number spoke about the entire subshell. Right, magnetic quantum number spoke about the orbitals which are present inside. Okay, now if you check it out, till now no one discussed about the electrons present inside. We know the electrons are present inside the orbital. Right, electrons are present inside the electron orbital. So the fourth level. By now, until the discovery of all these three, no one spoke about in which direction they are moving, something like that. They didn't discuss. Right, because of this, few things in science were surprising. There were no answers for few things, right? Though the discovery of all these three quantum numbers come along, but few things are giving surprise to all the science people, right? What is that one? One of the things which surprised the science people is nothing but they could not account for the peculiar behavior of alkali and alkaline earth metals, right? You know, 1A group elements, 1A group elements in the long form of periodic table. In the same way, 2A group elements of the long form of periodic table, entire group elements which are called as alkali, and second group element, this is the first group and this is the second group, right? They are having some peculiar behavior, right? Now, all these quantum numbers, they could not account for that. What's the reason for the peculiar behavior? Why they are behaving like that? Why? Because right, all these three, they didn't talk about the behavior of the electrons in the orbital. But keep it aside, we will talk about that one. So, what is, okay, I said who are making that peculiar behavior, I said, but what is the peculiar behavior? What is that strange behavior? The strange behavior is, example, you take sodium, right? Sodium is one of the elements of this family, alkaline, one is S group elements, all these, they come and see here, this is the general configuration of alkali, NS1, in the same way NS2. As we are having, right, you can check it out, it's nothing but S and S, we call them as S block elements, right? There, the sodium is one of the S block elements belonging to 1 and 2 group. So, they are exhibiting yellow color light. Generally the light has a white color, right, or whatever it might be, no color for that one. But in few situations, like you take sodium vapor lamps, sodium vapor lamps, they are emitting something like yellow color, right. This we can see in something like street lights, right. We can see in street lights. Right. Why? What's the reason? Why the light is emitting yellow color? Right. What's the reason for that one? This reason was not explained by the 3 quantum numbers which are known by that time. So to answer this, when the scientists were working on later on, an answer has been founded by in the spin quantum number. That's the reason why the spin quantum number is introduced. So answer is right. I will come back to the explanation, but why it is introduced means to answer the strange behavior of S block elements, especially alkali and alkaline earth metals, why they are emitting yellow color light. To answer this, our quantum number, spin quantum number is the questions raised regarding the properties of the electron, which were not explained by the other 3 quantum numbers, principal, azimuthal, and magnetic quantum number. That questions were solved by spin quantum number. Now, what does the spin quantum number say? Right. So let's come back to this one. Spin quantum number explain the properties of the electrons in the orbital. Explain the properties of electrons. Explain the properties of electrons in the orbital of elements in the orbital. This is the main thing. Whereas principal, they were talking about the orbits, subshells and orbitals, but they didn't talk about the electrons in the orbital. That's the very important. So who introduced this? Uhlenbeck and Goudsmit. They have introduced in the year 1920. And how it is symbolized? We are having 2 symbols here. We can call it as M as subscript S, or mainly as S. So that is the symbol. Now generally the principal quantum number takes values of all positives. Azimuthal quantum number take values of all positive with the 0. Right. Magnetic quantum number takes positive and negative and also with the 0. But this is the strange thing that the spin quantum number takes the half integer values. The remaining all are integers. You have to remember this one. The remaining all are integers, whereas spin quantum number takes half integers, right? So that too, it is nothing but plus half and also minus half. These are the 2 values. Moreover, all the other quantum numbers, right, azimuthal quantum number depended on principal quantum number. Magnetic quantum number depended on azimuthal quantum number, whereas spin quantum number doesn't depend on any other quantum number. It is, right, intrinsic behavior of an electron, the natural behavior of the electron. It has a specific value. So he has assigned, right, Uhlenbeck and Goudsmit in the year 1920, they have assigned the half integer values for the electrons. So of course everyone knows that there are 2 electrons in each orbital. 2 electrons in each orbital, right? If you talk about a single orbital, we are having 2 electrons there. Right, so now, right, these 2 electrons were given 2 spins. One is clockwise, the other one is anti-clockwise. So the 2 electrons which are present in each orbital as assigned 2 directions, one in the clockwise, the other in the anti-clockwise. Now let's get back a little bit deep about the spin, how they are indicated, what are the values given, and all with the help of the values here. Now, if you check it out, I am giving the value for you here. The half integer. Now, what are the 2 spins what we have introduced? It's nothing but the clockwise direction and the anti-clockwise direction. These are the 2 directions we are given. Now, half integer values. Just now I said we have given half integer values. For what it is given what? For clockwise direction, the half integer value is nothing but a plus half. right? This is the value introduced, and for the anti-clockwise, it has given the ms value is nothing but minus half. These are the values. Half integer, what values are assigned means for clockwise direction they had given positive plus half, and anti-clockwise direction they had given minus half in the spin quantum number. Now, how they are represented? Here we can call, right, if you go upward, right, as it is in the clockwise direction, now it is represented like this. See the arrow mark here, it is going in the clockwise direction, right? The clockwise direction, it is the upward direction is there, and it is nothing but the direction in which we are showing there. It moves towards the clockwise, right? In the same way, if you go to anti-clockwise, the arrow mark is denoted like this, right? And the direction goes, as it is going in this direction, now it goes in this direction, right? This is the direction indicated, right? So if you check it out, this is the clockwise direction, that is the anti-clockwise direction. Of course, you can also call this as spin up. We can call this as spin up, and we can call that as spin down. These are the two names which we can give it to the right. These are the clear explanations or assigning the values and the symbols for both the clockwise and the anti-clockwise direction. If you check it out, half integral values, clockwise direction is given positive plus half, and anti-clockwise direction it is given as minus half. Now the representation, the arrow mark is pointed upwards, that's why we are calling it as spin up. Now the second electron, this we can call it as for the first electron, the other one we can take it as for the second. It depends. If there is only one electron, it matters. If there are two electrons, they should have these things, right? A spin up and spin down, there it is nothing but a clockwise rotation and anti-clockwise direction. These are now basing upon all these values. We set up, just now I was talking, if we are having only one electron, no issues. It may be having this or it may be having this, basing upon the situation. But if there are two electrons in the orbital, what kind of spin they have, what are the possibilities they have, let us figure it out. So the possibilities, assigned two possible spins. One is nothing but the parallel spin. When do you call it as parallel spin? When both the electrons are facing up. Right, when both the electrons are going in the same direction, then we call it as a parallel spin. That's what. So here the values will be, for the first one also we are having plus half, and the second one also we are having plus half. Are you able to? So parallel spin means when they are moving, when both are moving in same direction, we are taking it as right, then we call it as parallel spin. Okay, now let's get back to the other possible spin assigned with the help of those when we are having two electrons. The other one is, right, one facing upwards and the other facing downwards. Okay, so this we call it as anti-parallel spin. One moving in the clockwise direction, the other moving in the anti-clockwise direction. If you assign the values, the first one will be positive half and the second one will be negative half. Okay, now what kind? You have to remember, they are moving in opposite direction. This is right, opposite direction. So these are the possibilities. These are the brief introduction what Mr. Right, Ulenbeck and Goudsmith they had given in the spin quantum number. But please remember, all these came forward to give explanation for the peculiar behavior of alkali and alkaline earth metals, which was not explained by other quantum numbers. So how did they clarify? We'll come to know. But let's go for this one. Right, they explained the properties of the electrons, introduced symbol, half integral values, but please remember the remaining all are integers, and spin quantum number, it's a peculiar behavior or the intersect character of the electrons in the orbital. This property does not depend on any other quantum numbers, right? Two possible directions, clockwise and anti-clockwise, and here it is clearly detailed how they are moving. Now the possible directions or orientations or the spins is nothing but a parallel spin and anti-parallel. Yeah, what is the explanation given by Mr. Spin in the spin quantum number by Uhlenbeck and Gauss-Spin for the strange behavior of alkali and alkaline earth metals exhibiting light or emitting light which is in yellow in color, right, which others could not explain. So let's go for that one. Explanation for the behavior of alkali, which are nothing but general electronic configuration NS1, they are of 1A group elements. In the same way, alkaline earth metals general electronic configuration is NS2 for all the second A group elements in the periodic table, right? If you go for the periodic table, as you all know, right, this is nothing but 1A and this is nothing but the 2A in the entire periodic table, right? So you know that this is the periodic table what we generally take, right? So these are nothing but the alkali whose electronic configuration is NS1 and the second one is NS2. If you think about the periodic table, entire NS1 and NS2, right, they are having this peculiar behavior. So what is the reason given by them is nothing but, right, Uhlenbeck and Gauss-Spin, they are saying that it's a peculiar natural behavior of the electrons, right, especially of those, right, the intrinsic or natural behavior of the electron to exhibit of that group. That is the natural behavior. So that's the first point. So it's a natural behavior, and very importantly, it comprises of closely spaced duplet of electron. This matters electron. What is the meaning of duplet here? Let me explain you the concept of duplet here. Okay, D-O-U-P-L-E-T, duplet structure. Let me explain you the duplet structure here. Right, so any structure which is having half integral value, like let me go for this. Let me go for an example of an orbital which is having, right, upward direction and also the downward direction and something like this, right? If we are having any electron pairing like this structure, if you check it out, here it is nothing but plus half and this is nothing but minus half, balanced here, whereas here we are having only half. So can I call this one as, it's nothing but half integral or integer values, right? So now any such a structure which is having one complete pair and one unpaired, one complete pair and one unpaired, if you are having, and the last one, if you are having an half integral, it might be a positive integral or a negative integral, it may be a clockwise or anti-clockwise. If the last one is left over like this, such a structure we call it as duplet structure. Right. So what Mr. Spin in the spin quantum number, what he's saying means any duplet structure has the property of exhibiting that peculiar behavior or exhibiting yellow color light. Right, this is right. That's what comprises of closely spaced duplet of electron. Let me go back a little bit clearly with one more example. Let us take helium. Right, helium, I picked a hydrogen helium, I have taken an element from to 1A group. Okay, I have taken an element from 1A group. Now, what's the electronic, right, atomic number of that one? Hydrogen, helium, lithium, it's nothing but 3. Right, atomic number is nothing but 3. Now, what's the electronic configuration? It's nothing but 1s2 and 2s1. This is the electronic configuration. So, I repeat, helium, atomic number is 3, electronic configuration is 1s2, 2s1. Now, let's go with the pairing up of the electrons. Okay, now as 2 electrons are there, now I have paired it with one in the clockwise direction, the other one in the anti-clockwise direction, whereas the other one, the third electron, will be having something like clockwise or anti-clockwise, but unpaired. Here it is balanced with the positive half and negative half, whereas this is left over with either positive or any one half. Here I am taking it as clockwise direction. Now helium is having duplet structure, and helium is an element of 1A group, alkali. Alright, in the same way, let us go with one more example. Right, let me take an example of sodium. Let us take the example of sodium. Again, atomic number of that one is 11. Electronic configuration is nothing but 1s2, 2s2, 2p6 and 3s1. Okay, now if you check it out again, right, I am drawing only here it is. If you go right here, it is 2, again it is with the 2, no issues there. Where if you go over the 6, right, 2p6, it's nothing but we are having 3, 1, 2 and 3, 4, 5, 6. Whereas everything is paired up. Now if you go for the last one, it's nothing but only 1, 3s1. So here it is completely filled, whereas that is half filled, right? Any such a structure, we call it as duplex structure. Right, so because of the duplex structure of these elements, especially in the alkali and alkaline earth metals, they are having the peculiar behavior of emitting yellow color lights. Now one more example, right, moreover, when the light rays is coming from this one, the light rays which are coming out, their frequency is very close to the yellow color character, right? That's what I repeat. In the example you take, right, the street lights, right? If you take the street lights, right, when the light is coming from the yellow, right, the street lights, the wavelength, you know what's the meaning of wavelength, right? The wavelength, whatever it is coming, it is close to yellow color. Right, you know with CR, right, we are having frequencies for each light, right, each color we are having a wavelength from ranging from here to here. The light rays which are coming from the sodium vapor lamps, those the wavelength of those light is very close to the yellow color light, or the frequency or the wavelength of the yellow color. That is also one of the reasons given for Mr. Udenbeck ground spin in a spin quantum number. Thus, all these explanation, intrinsic character of the electrons, and they are having duplex structure, and the wavelength emitted by the sodium vapor lamps are very close to the yellow color light frequency or wavelength. Because of these factors, yes, they are having the peculiar behavior answered by spin quantum. Yeah, the importance of the spin quantum number can be observed more in knowing fermions, bosons, and in multi-electron structure or multi-electron system. So, what are these fermions? Right, particles with half integer values. Right, you have to remember this one. What are fermions? So, right, particles with half integer values. Like example, I like to give just now duplex structure. So, one in the upward, one in the down, and right here, if you check the values, here it is nothing but plus half, and here it is minus half, whereas it is only plus half. All such particles who are having that kind of structure are called as fermions, right? Of course, it's nothing but duplex structure, right? All those ions, right, we can figure it out with the help of spin quantum number. The next one, as we are able to figure it out, the fermions which are having the half integral function values, let's now bosons are nothing but particles with, right, of course, full or just integer values. Right, integer values, like any structure which is in this model, right, the up spin, down spin, in the same way, right? Here it is nothing but plus half and minus half, again plus half and minus half. It's nothing but a whole integer. You can go for this for 0. Now, what is multi-electron structure? any, right, like it might be a basin or a fermion, if it is having many number of electrons, right, the spin quantum number will be helpful, because no two electrons will be having same energy in the entire atom, basing upon the rule that no two electrons in the atom, right, no two electron in the atom has same energy, multi-electron system can be figured it out. So this rule will be very useful for us in filling the electronic configuration. So with the help of all the four quantum numbers, right, spin, right, magnetic, and angular momentum or principal quantum number, we can arrange the electrons, right, in different orbitals in a systematic manner, which is called as electronic configuration. We will come forward with those topics now. Thank you. In this channel, I have been placing both math and science videos.